Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to talk on the module Hybridization in Carbon-Based Molecules from the paper Physics at Nanoscale. So students, let us see what we are going to learn in this module. First, we will study the Sp2 hybridization in methane. Next, Sp2 hybridization in ethene. Thirdly, we will also discuss the Sp hybridization in acetylene. Lastly, we will also discuss the hybridization in benzene molecule. So students, let us start with a basic introduction about the module. The materials, clusters and molecules based on carbon, they are unique in many ways. The most important distinction is the existence of several possible configurations of the electronic states of a carbon atom in different carbon-based systems. The different configuration resulting different topology is known as the hybridization of atomic orbitals. Hybridization is a concept based on mathematical treatment of the wave functions of atomic orbitals to give new wave functions representing hybrid orbitals, which are very useful in the explanation of molecular geometry and atomic bonding properties. Only orbitals of similar energies, they can be mixed together to form stable hybrid orbitals. The number of hybrid orbitals produced equals the number of atomic orbitals mixed together. The concept of hybridization was first introduced by Linus Pauling to explain the structure of simple molecules such as methane using atomic orbitals based on experimental findings that there are 4 CH bonds with a bond angle of 109.5 degrees between each other. Pauling pointed out that a carbon atom forms 4 bonds by using 1 s and 3 p orbitals. Carbon is the 6th element of the periodic table and there are 6 electrons in a carbon atom which occupies the 1s2, 2s2 and 2p2 atomic orbitals. The first 2 electrons, they are strongly bounded electrons and they occupy the 1s2 orbital and they are designated as the core electrons. The remaining 4 electrons, they are weakly bounded electrons than the core electrons and they are known as valence electrons. In the crystalline state, the valence electrons give rise to 2s, 2px, 2py and 2pz orbitals, which take part in the formation of covalent bonds in carbon materials. So as the energy difference between the upper 2p energy level and the lower 2s level in carbon is small as compared to the binding energy of the chemical bonds, the electronic wave functions for these 4 electrons can readily superimpose and change the occupation of the 2s and 3 2p atomic orbitals, thereby enhance the binding energy of the carbon atom with its neighboring atoms. So the superposition of 2s and 2p atomic orbitals is called as hybridization. Generally, the mixing of a single s electron with different number of p orbitals, that is n can be 1, 2, 3, p electrons is called Sp2 hybridization. For a carbon, in general, there are 3 possible hybridizations, that is Sp, Sp2, Sp3, which we will discuss in this module. So now students, let us discuss the Sp3 hybridization. CH4 is the best example exhibiting the Sp3 hybridization. In CH4, there are 4 covalent bonds. So, the carbon have 4 orbitals with the correct symmetry to bond to the 4 hydrogen atoms. Now, as we all know that the carbon's ground state configuration is 1s2, 2s2, 2p2, which can be represented by this, that is, we have 2 electrons in 2s and 1, and basically 2p have 3 components, px, py, pz, and so px, py have 1 electrons. Now we have 2 experimental findings, that is, the CH4 has 4 identical CH bonds and the bond angle between them is around 109.5 degree. The carbon atom can use its 2 singly occupied p-type orbitals to form 2 covalent bonds with 2 hydrogen atoms, yielding the methylene CH2, which is an unstable molecule. To form a stable molecule with hydrogen atoms, carbon atom can also bond to 4 hydrogen atoms by an excitation of an electron from the doubly occupied 2s orbital to the empty 2b orbital, resulting in 4 singly occupied orbitals. And this is shown by the electronic configuration of C star, which is nothing but the excited state of carbon. On the right hand side, you can see the shape of different orbitals in a carbon atom. That is, these orbitals are 1s corresponding to first shell, and the second shell has the orbitals like 2x, 2px, 2py and 2pz. So now the energy which is released by the formation of 2 additional bonds compensates the energy which is required for exciting 1 electron from 2s to 2p, energetically favoring the formation of 4 CH bonds. It can be shown that the lowest energy is obtained if the 4 bonds are equivalent, which is possible if these 4 bonds are formed from the equivalent orbitals on the carbon. A linear combinations of the valence shell, that is S and the P wave functions, is the best possible choice for the set of 4 equivalent orbitals, which are the 4 Sp2 hybrid orbitals as shown in the electronic configuration of C star, where there are 4 hybrid Sp2 orbitals resulted by a linear combination of 1s and 3p orbitals. As it has been discussed before, there is a small energy gap between the 2s and the 2p orbitals as shown in the figure below, and so a small amount of energy is required to promote an electron from the 2s to the empty 2p orbital. When the bonds are formed, the extra energy released not only compensates for the initial cost of energy, but also lowers the total energy of the molecule. All this representation of the gain in the energy in the formation of 4 hybrid orbital sp3, which is resulted by a linear combination of 1s and 3p orbitals, is shown in this figure. When 4 sp3 orbitals are formed around the carbon atom, they arrange themselves to avoid each other, resulting a tetrahedral arrangement with an angle of 100.5 degree. When the hydrogen atoms combine with the carbon atom to form a CH4 molecule, it also becomes a tetrahedral with 109.5 degree bond angles. The carbon atom in methane, that is CH4, provides a simple example of sp3 hybridization through its tetragonal bonding to 4 nearest neighbor hydrogen atoms. In order to make the elongated wave functions to the 4 directions in tetrahedral configuration, the 2s orbital and 3 2p orbitals are mixed with each other, forming the sp3 hybridization, and orthonormal atomic wave functions for sp3 hybridized orbitals in these 4 directions are given by, that is, we have spa3 equal to half of 2s plus 2px plus 2py plus 2pz. sp3b equal to half of 2s minus 2px minus 2py plus 2pz. Next is sp3c, which is equal to half of 2s minus 2px plus 2py minus 2pz. Lastly, we have Sp3d, which is equal to half of 2s plus 2px minus 2py minus 2pz. In general, for Sp(n) hybridization, n plus 1 electrons belongs to the carbon atom occupied in the hybridized sigma orbital and 4 minus n plus 1 electrons in the pi orbitals. Now let us discuss the Sp2 hybridization. There are other carbon-based compounds and molecules which have double bond between the carbon atoms, such as ethene, that is C2H4, which is represented by CH2 double bond CH2. The experimental findings are it has a planar molecule with 4 identical CH bonds as shown in this figure and 1 C double bond C bond, and all bond angles are approximately equal to 120 degree. For these molecules, carbon atoms are Sp2 hybridized because one pi bond is required for the double bond between the carbons. In Sp2 hybridization, the 2s orbital is mixed with only 2 of the 3 available 2p orbitals, forming a total of 3 Sp2 orbitals with 1 remaining the p orbital. As it has been discussed that in the ethene molecule, the 2 carbon atoms forms a sigma bond by overlapping 2 Sp2 orbitals, and each carbon atom forms 2 covalent bonds with hydrogen by S-Sp2 overlap with 120 degree angle. The pi bond between the carbon atoms perpendicular to the molecular plane is formed by 2pz overlap. The hydrogen-carbon bonds are all of equal strength and length in agreement with the experimental data. Now let us discuss the Sp2 hybridization. There are other carbon-based compounds and molecules which have double bonds between the carbon atoms, such as ethene. For these molecules, carbon atoms are Sp2 hybridized because there is one pi bond is required for the double bond between the carbons. In Sp2 hybridization, the 2s orbital is mixed only with 2 of the 3 available 2p orbitals, forming a total of 3 Sp2 orbitals with 1 remaining the pi orbital, or with 1 remaining the p orbital. So the experimental findings of this ethene molecule are that it is a planar molecule with 4 identical CH bonds and 1 C double bond C, and here all the bond angles are approximately equal to 120 degree. In ethylene molecule, 2 carbon atoms form a sigma bond by overlapping 2 Sp2 orbitals, and each carbon atom forms 2 covalent bonds with hydrogen by S-Sp2 overlap with 120 degree angles. The pi bond between the carbon atoms perpendicular to the molecular plane is formed by 2pz overlap. The hydrogen carbon bonds are all of equal strength and length in agreement with the experimental data. So this shows the electronic configuration of the excited state of carbon, that is C star, in Sp2 hybridization, and the below figure shows the schematic configuration or the representation of the formation of 3 Sp2 hybridized orbital, leaving one unhybridized p orbital for one pi bond. In Sp2 hybridization, the 2s orbital and 2p orbitals, for example 2px and 2py, they are hybridized. In Sp2 hybridization, all the sigma bonds are lying in the xy plane, that is as it is shown in this figure, and in addition the pi orbital for each carbon atom exists perpendicular to the plane. As shown in the next figure, that we have the Sp2 1s head-on overlap, that is we have the 4 identical CH sigma bonds, and there is the overlap of Sp2 orbital and the 1s orbital. Now the 3 Sp2 hybridized orbitals are made from 2s, 2px and 2py orbitals, and they are given by Sp2a is equal to C1 2s minus root of 1 minus C1 square 2py. Sp2b is equal to C2 2s minus root of 1 minus C2 square multiplied by root 3 by 2 2px plus half 2py. Sp2c is equal to C3 2s plus root of 1 minus C3 square multiplied by bracket minus root 3 by 2 2px plus half 2py. Now here the coefficients C1, C2 and C3, they can be determined from the orthonormality of the Sp2i and 2s, 2px, 2py orbitals, and we obtain 3 equations for determining the coefficients C1, C2, C3, and these equations are C1 square plus C2 square plus C3 square equal to 1, C1 C2 minus half multiplied by root of 1 minus C square multiplied by root of 1 minus C2 square equal to 0. C1 C3 plus half multiplied by root of 1 minus C1 square multiplied by root of 1 minus C3 square. Now all these equations result in the solution of C1 equal to C2 equal to 1 by root 3 and C3 is equal to minus 1 by root 3. The Sp2 orbital thus obtained have large amplitude in the direction of the 3 nearest neighbor atoms, and these 3 directed orbitals are denoted by trigonal bonding. So as you can see in this figure, we have a 1s orbital, 2px and 2py orbital, and after Sp2 hybridization they gets elongated along a certain direction, and all these are joined together and they are inclined at an angle of 120 degree. That is, each Sp2 hybrid orbital has 1 by 3 s character and 2 by 3 p character. Now on the right side figure, we have the orbital overlapping for C2H4 molecule. That is, there is the overlapping of this sp2 orbital. So students, let us now discuss the ethylene molecule, which is represented by CH double bond CH. So basically, experimentally, it has been came to the conclusion that the ethylene molecule is a linear molecule with identical CH bonds and one C double bond C bond. So we have CH triple bond and then CH. So this is represented as shown over here by the linear sp hybridized configuration. Now continuing our discussion over sp hybridization, that is, here we are discussing the C2H2 molecule, that is ethylene or acetylene. Now here the chemical bonding in this molecule with triple bonds between the two carbon atoms is explained by sp hybridization, in which the 2s orbitals is mixed with only one of the three p orbitals, resulting in two sp orbitals and two remaining unhybridized p orbital, as shown in the electronic configuration of the excited state of carbon C star in sp hybridization. The chemical bonding in C2H2 is explained by sp hybridization, which consists of sp-sp overlap, as shown in these below figures, between the two carbon atoms, forming a sigma bond, and two additional pi bonds formed by pp overlap, and each carbon atom bonds with the hydrogen atom through a sigma s-sp overlap at 180-degree angle. So in this hybridization, there is a linear combination of the 2s orbital and one of the three 2b orbitals of a carbon atom is formed. From the two electron orbitals of a carbon atom, two hybridized sp orbitals, which are denoted by spa and spb, are expressed by the linear combination of 2s and 2px wave functions of the carbon atom as spa is equal to c1 2s plus c2 2px and spb is equal to c3 2s plus c4 2px, where ci are the coefficients, and using the orthonormality conditions, which are spa spb is equal to 0, spa spa equal to 1 and spb spb equal to 1, and we obtain the relationship between the coefficients ci, c1 c3 plus c2 c4 equal to 0, c1 square plus c2 square equal to 1, c3 square plus c4 square equal to 1, and c1 square plus c3 square equal to 1. The last equation is given by the fact that the sum of 2s components in spa and spb is unity, and the solution of above equations gives us c1 equal to c2 equal to c3 equal to 1 by root 2 and c4 is equal to minus 1 by root 2. So the equations becomes spa is equal to 1 by root 2 2s plus 2px, spb is equal to 1 by root 2 2s minus 2px. the formation of pi and sigma bonds in C2H2 molecule have the strength of the pi bond between two pz orbital, which is maximum when pz orbitals are parallel to each other, resulting in linear molecule with an angle of 180 degree between CH SPX bond and C triple bond C. Now if we have the 2py sideway overlap as shown in this figure, then there is a C single bond C pi bond, and the right side figure shows 2pz sideway overlap, implying a C single bond C pi bond. Now as you can see, students, over here, that if the s orbital and the px orbital, that is s and p, they are joined together or giving rise to the sp hybridization, resulting in the inclination of them by 180 degree, and here each sp hybrid orbital has 50% s character and 50% p character. Now students, let us discuss the hybridization in benzene, that is C6H6. This figure shows the electron density map or the symmetrical distribution of electrons. Now benzene. Benzene is a planar molecule consisting of 6 hydrogen atoms and 6 carbon atoms. Each carbon atom has to join 1 hydrogen and 2 carbon atoms, so doesn't have enough unpaired electrons to form the required number of bonds. To achieve this, each carbon atom has to promote one of the 2s2 pair into the empty 2pz orbital. Experimentally, it has been found that from XRD that all the 6 carbon-carbon bonds in benzene are of the same length at nanometer, which is greater than a double bond 0.135 nanometer but shorter than a single bond, which is 0.147 nanometer. This intermediate distance is consistent with electron delocalization, that is, the electrons for C single bond C bonding are distributed equally between each of the 6 carbon atoms. So we can interpret in terms of valence bond theory. We have the step 1, that is to obtain the most stable Lewis structure. So this shows the Lewis structure, and the real structure is the resonance hybrid of the 2 resonance structures, which is implying that each C single bond C has 50% single bond character and 50% double bond character. In the step 2, that is type of hybridization of carbon. Now there are 3 negative centers around each carbon atom, which are trigonal planar and exhibits the Sp2 hybridization. Now consider firstly the sigma framework. First case, if we have the Sp2 and 1s head-on overlap as shown in this figure, that is, this has 6 identical CH sigma bonds. The second case, if we have the Sp2 head-on overlaps, which has 6 identical C single bond C sigma bonds. Now let us discuss the pi framework, where we have the 6 unhybridized 2p z orbitals which are perpendicular to the molecular xy plane. And the second case, if we have the 2pz sideway overlaps, this implying the three identical C single bond C pi bonds. Now, as shown in the right hand side, that all these hybridized orbitals or the framework, they are almost identical with each other. Delocalization of pi electrons, which is governed by MO theory. Now here there are 6 2pz orbitals which overlap with one another to give a continuous pi electron cloud above and below the molecular plane. In fact, the combination of 6 2pz orbitals give rise to 6 molecular orbitals. The most stable bonding molecular orbital which can accommodate only 2 electrons. Now let us discuss the driving force for delocalization of pi electrons. First, there is more space for electrons to distribute within the molecule, and the repulsion between the electrons is minimized. Secondly, the electrons can be attracted by more than 2 nuclei at the same time. Now let us discuss the hybridization in carbon compounds. In carbon-based compounds and solids, the hybrid atomic orbital model can be extended to the molecules by including valence shell d orbitals, and resulting shapes are called trigonal, bipyramidal or octahedral. Generally, when the 3dz2 orbital is mixed with 3x, 3px, 3py and 3pz orbitals, the resulting Sp3d hybrid orbitals point towards the corners of a trigonal bipyramid, and when both the 3dz2 and 3d-dxy 2 orbitals are mixed with 3x, 3s, 3px, 3py and 3pz orbitals, there will be a set of 6 sp3d2 hybrid orbitals basically that point towards the corners of an octahedron. All these possibilities with different pair of carbons and other elements in different carbon-based compounds, they are given in this table. That is, this shows the relationship between the hybridization and the distribution of electrons in the valence shell of an atom. Now students, let us discuss the rules for identifying the type of hybridization of a central atom in a given species. First, we work out the most stable Lewis structure of the species. Second, predict the molecular shape of the species with respect to electron pairs around the central atom. Lastly, match the predicted molecular shape with the type of hybridization according to this table. So students, let us summarize what we have learnt in this module. Firstly, the carbon atom in methane provides a simple example of sp3 hybridization through its tetragonal bonding to the 4 nearest neighbor hydrogen atoms. Secondly, in ethene molecule, 2 carbon atoms forms a sigma bond by overlapping the 2 sp2 orbitals, and each carbon atom forms two covalent bonds with hydrogen by sp2 overlap with 120-degree angles. Thirdly, the chemical bonding in acetylene can be explained by sp hybridization, which consists of sp overlap between the two carbon atoms, forming a sigma bond, and two additional pi bonds which are formed by pp overlap. Next, the benzene. It is a planar molecule consisting of 6 hydrogen atoms and 6 carbon atoms. Now here, each carbon atom joins with 1 hydrogen and 2 carbon atoms, and it doesn't have enough unpaired electrons to form the required number of bonds. Lastly, we also discussed the carbon-based compounds and solids, in which the hybrid orbital model can be extended to molecules by including the valence shell d orbitals, and resulting shapes, they are called trigonal bipyramidal or octahedral. Thank you.